It's the oops all collisions group. We wanted to make a program that efficiently calculates collisions for thousands of entities, concurrently and in real time. So that's our project. You can see it was kind of a little bit of a complicated project with 153 comments. And actually, if I actually check, I think I clocked this. Yeah, it's also 2,500 lines of code. Yeah, but our design for this was pretty involved. We took a very interface heavy approach because we kind of wanted everything to be independent of each other. So, for example, if you look at container interface, it contains all the stuff that you'd need. There's a little bit of cursed right here, but we have a lot of virtual functions that we actually go in and implement it so we can bind all of our data structures to this container interface. Same thing with this render interface. So another example is with this render interface, we made it a point to keep the rendering and all that sort of stuff with Raylib. We're actually using Raylib for our rendering. We kept it independent of our core library. So actually, with this null render, for example, here, like you could just implement your own renderer and text and like mouse handlers and that sort of stuff. And it's quite literally just plug and play. So that's pretty cool. Yeah. Looking at the actual project, the main file we're concerned with is simulation main. At least that's what I use to generate the videos that you're going to see pretty soon. And basically, you can choose a data structure. We have 4 supported. We were going to be bounding volume hierarchy, but that one's hard, and we ran out of time for that one. So you're trying to get 4. The naive linear is just a vector of all the entities, and it does a O of n squared comparison, so it compares every entity to every other entity, apart from itself, obviously. And the spatial hash, it uses a hashing function on the position to generate a cell that it's in. So to check for collisions, all you do is you check the cell that your entity belongs to and the 8 neighboring cells for any collisions. We also have multi-level grid. This is actually a quad tree that expands and contracts depending on the elements inside. It's a dynamic tree. And then we also have sweep and prune, which is kind of similar to naive linear, except it's way faster because it stores all the entities. It stores the start points of the bounding boxes and the end points of the bounding boxes, the x coordinate, in a sorted list, right? So if you want to, figure out all the collisions, you just sweep across the list, and you keep a list of all the bounding boxes that you haven't hit the end of, and basically you can get a list of all the active collisions. So to demonstrate how this works, you choose a data structure. As I originally said before, we have an interface for this, so it doesn't matter which one you choose. They all behave the exact same way, so I'm just going to change it to spatial hash. And then also we have a constants, because I could not be bothered to go and change all the const experts. So for the simulation, we'll say like 500. All this stuff is configurable. Like, this is just I found to be good numbers, but yeah, we can run the executable. It'll build. You get this nice title screen that we made. It's actually controlled by a state machine, which is way overkill. Some parts of this project are overkill. We like over-engineered some parts of the project and under-engineered other parts, so that's how you can tell it's a good project. But yeah, you just click to begin it, and yeah. So if you notice, like, they actually are colliding with each other, right? With coefficient restitution of 1, and you can see I have it so it highlights the cells. The quad tree will highlight the nodes, but yeah, this actually calculates the collisions, real world collisions. Oh, can we get that one? Boom, collision. Yeah. So yeah, you can escape it that way. Oh, I gotta close this out. Let's see. Is there anything else I need to ramble on about? I think that mostly covers everything, but I also have prepared a little bit of a showcase for you, so I hope you enjoyed that. Thank you.
As you would expect, none of them struggled with 100 entities. Sweep and prune is in the top left. The naive linear algorithm is in the bottom left. Then you have the quad tree and spatial hash on the right. I was pretty surprised in how well everybody performed on 1,000 entities too. Oh, and by the way, all of this is rendering in real time, so any lag you see is because of the data structure. 5,000 is where you start to see a lot of slowdown. You can start to see the quadratic nature of the linear algorithm. I was pretty disappointed in the quad tree, but that's to be expected because you have to traverse down the entirety of the tree for every single node.
Out of all the data structures, spatial hash performed the best, and that's because this problem is very well suited to hashing functions in terms of like cell coordinates and whatnot. I tried to make it a little more suspenseful with that little bit of an intro, but yeah, spatial hash did perform the best.